next minute or two, but let me wish you all a very warm welcome to the NASA's Waste Jettison Mechanism Winners Webinar. We're really excited to share some of the winning concepts with you from the past few months of work. And we've got most of the winners here to display to give their own presentation on what they envision for this challenge. We'll have an opportunity for a little bit of Q&A later too. So if you haven't seen already, or you don't know how Zoom webinars work, we have a little Q&A button at the bottom of your screen here. I ask that you enter your questions there as opposed to the chat, because the Q&A is where we're able to actually see them and bring them forward to the crowd. So yeah, please feel free to enter your questions to that box anytime. I'll give a reminder for that later on. Let's just give it one more second here as some people join. In the meantime, though, you're very welcome to enjoy this nice slideshow we have that's going to accompany this whole presentation. For the second slide, if you want to advance it there, we're going to learn a little bit about, thank you, our winners here in a moment. Before we do that, though, why don't we start with an introduction to our NASA team. Mike, do you mind giving us a quick intro to yourself?
No problem. I'm Mike Ewert at the NASA Johnson Space Center. I've been working here over 30 years. And right now working on a project called Logistics Reduction on long space missions.
Excellent, thank you. Mike has been one of our fearless sponsors of this challenge with us for many months from beginning to end. And it's been a joy working with you and getting to score these together. Second, we've got Ryan here, who's not actually part of the specific team on this challenge. He helps with all kinds of challenges, but go ahead, Ryan.
Sure, thanks. Hello, I'm Ryan Stewart. I'm the Deputy Program Manager of a team called COSI, the Center of Excellence for Collaborative Innovation. And we host the NASA Tournament Lab. You've probably seen quite a few, if you paid attention to a lot of the HeroX challenges, quite a few things coming from the NASA Tournament Lab. And so we are really the in-between group that helps folks like Mike and his coworker Steve get their really hard problems to you all to help solve. And so we're the ones that are really your voice at NASA itself. And so I'm happy to be here and I'm excited to see all the great solutions.
Absolutely. And thank you for bringing this great challenge to the world.
Shane, just to let you know, our colleagues from the Ames Research Center out in California, Steve Sepka and Justine Richardson, they had some trouble getting on today, so we'll hope to get them in.
Excellent. Thank you, Mike. Well, once they hop in, we'll certainly include them in the discussion. Yeah, Steve and Justine were also essential to this challenge, along with many others who wouldn't be able to be on this call as panelists, but big thanks to all of them for their hard work. And so I didn't mention myself, but my name's Shane Jenkins. I'm a project manager at HeroX, and I was assisting this challenge from its creation to its running to the winner selection. So I've been here talking to the winners and all the other competitors in the background. And so it's fun to finally get to put some spotlight on them for once and get them into the public. And with that, do you mind advancing to the next slide? And we'll allow our first place winner, Jason. Can you give your introduction, please?
Sure. Hello, everyone. This is Jason McAllister. I am from Jacksonville, Florida. And I'd just like to say this is a great honor to have received this. It's a privilege to have been able to compete with all these great solutions that I've seen. I appreciate the time and consideration the judges have had. I know they've had to go through a lot of submissions, and if they're anything like mine, they've had to read probably hundreds of pages, thousands of pages. And it was a great privilege to meet the judges on the finalist panel and to see their perspective and their point of view and their questions that they had regarding the submissions. It was very exciting, a very unique experience. And I'd like to thank HeroX and Shane for all of the help you've done walking us through the details of this. So just a little bit about me. I've participated in several NASA competitions, NASA Tournament Lab, SOCOM, a few others, I think 6 total. So this is the first time I've won, I've placed. I've had honorable mention on the Venus. And I think, Ryan, I think you were on that video. I saw that one. So that had a lot of cool submissions, and it was neat how there were similar themes from submission to submission. On the Venus, submission, there were lots of triangular shaped tracks that seemed almost universal. And I've seen themes on this one too, which we'll see when everybody shows their demos. So my background, I'm not actually an engineer. I'm an MBA and I have a master's in health science. My hobby is maker. My focus is generally on electronics and robotics and the robot operating system, which was the topic of the space robotics competitions 1 and 2. Those were extremely interesting and you learn a lot. So when you have a deadline, you have to learn. It takes something off of your one day I want to know how to until I have to know by April 12th how to do this, or else I'm not going to be successful. So it's a great way to take your hobby and just push it up a level. And I'll say I almost dropped out of this competition about 2 weeks to go. My computer died and I spent a few days trying to resuscitate it. Couldn't do it. I had an emergency backup that was almost brand new. I only used 6 times. It would overheat and die every 30 minutes. Lost another 3 days. So finally, I bought another computer. I was balancing, should I rush? I knew I needed a new computer anyway, but should I rush it and have 1 week to do the final 50% of my submission? And I went ahead Saturday night, I bought it, spent that week. And then also I had to submit Sunday night. I couldn't wait till Tuesday because I was leaving town. So I barely made it. I shot up Monday morning, had a few other changes, updated my submission and left by 9 a.m. So it was very exciting right up to the last minute, but I've learned a lot and it's been just eye-opening, learning a lot about the waste jettison process. I didn't realize they just packed everything up with the capsule, sent it back. I assumed from watching movies, people just shoot things out, but that's not the case.
Well, that's a fascinating story, Jason. Thank you for that introduction. One, we love hearing cool stories like this, and 2, it's just hopefully you can actually pay for that additional laptop now that you've gone through this. So, okay, for our second place winner, Craig, do you want to give a quick introduction?
Yeah, hello. I'm Craig Payne, formerly in a former life. Before I retired, I did many things. I was in robotics as well as electronics technician, and I have a MS in IT. And however, I guess since I retired, I've taken my hobby as a aviator and became a mechanic as well, and that's pretty neat. And I got some spam. I'm sorry, but I was glad to enter this competition simply because it was so clear cut, as far as I'm concerned, as what the objectives were, and it allowed me to focus on a solution set. But easier said than done. I had to go back and reread the objectives and guidelines several times and through the process. But I had to do a lot of research, but all in all, I think I enjoyed this competition. I've done 8 of them so far, and I've got 3 wins. So maybe I'll make an ace one of these days. 5 kills.
We love to see repeat competitors, and thank you for your tenacity as well, Craig. Appreciate it. Our third place team is called Team Hypergroup. Ross, do you want to give an intro?
Hi, I'm Ross Palatan, and I am a second-year physics student from the Philippines. And also, this is Miko the Major. As you mentioned earlier, he's a game developer and software developer from the Netherlands. And then we have Benz Abraham from India, and he's a mechanical engineer. Also, fun fact, me and Miko actually also joined another competition from NASA. It's the other one, it's about the trash to gas competition, and we also won 3rd place. So that's it, yeah.
Congratulations. Yeah, we've got a lot of talent concentrated in this top group here. Thank you.
Thank you.
And then our next team, which tied for 4th place, is Team Aggie Arrows. And Krishna, was this your team's first competition?
Yes, this was our first competition. Personally, it wasn't my first competition, but as a team, this was. Right.
Excellent.
And so
Go ahead.
I'm a project manager. We're all basically just students from Texas A&M University. Our deputy project manager is Abigail. Our design team lead is Akshay. And then our logistics team lead is Carol. And then our safety officer is Victoria. And so our design team consists of Adarsh, Jason, and Garrett. And if you could go to the next slide, please. It also consists of Nick. And then our logistics team consists of Sean, Rashid, Marcus, and Aniket.
Excellent. Thank you for that introduction. Why not, if we go to the next slide, we can have our last fourth place tie, Jeff Morris, who's another frequent competitor and a winner of past challenges. He won't be able to join us for today's call, but he's given us a little bit of information and I can present the gist of his concept later on in this webinar. So just a quick intro for him. He's also has the website widgetblender.com, under which he does a lot of his competing. And if you want to learn more about Jeff, you can head to that website and there's a bit there you can read. Okay, next slide, please. And before we get on to these winning ideas, let me ask one quick question of Mike and Steve, or Justine here. So Steve and Justine, welcome. We gave a brief introduction to you before you could join today's call, but glad that you could join us, so thank you. The question I had for any of you, if one of you wants to jump in, is could you answer what it was like coming to crowdsourcing as a pathway to find a solution here? How was it different from the standard path you'd pursue? And then what was the motivation for this challenge in the first place?
Okay, I guess I'll go first. Oh, wait, let me allow my camera.
There you go. Thanks, Steve.
Yeah, I should be on now. So we're at the very beginning for these concepts, and the driving force was to get as broad ideas and perspectives on it that we really don't think we could come up with just a handful of people. So using crowdsource was really the way to go. I think it was a great experience and great ideas. Got to see a lot of different things we would never have thought of. And so as we start to move the process forward from the very beginning, we think we have a good background as far as the different ideas and concepts. And it looks really, really nice. So I'm very happy, and it's been quite a nice endeavor. So that's my take on it. I'll let everybody else jump in.
Yeah, this is Justine. Congratulations. You made it out of hundreds of entries. Is commendable in that way. Being a NASA researcher here, my attitude has been NASA, it belongs to America, right? It belongs to the world, space travel. And sometimes I talk to my friends and my family, people feel intimidated by NASA. They don't think that, they can contribute. But there are an incredible amount of resources out there. You guys are one group, as an example, who in order for us to make it to the moon, to the Mars, and explore space, we need all kinds of ideas, right? We don't have all the ideas, right? We're struggling with some ideas. And so I think I see crowdsourcing as an opportunity for the public to really participate in some of these things and know and kind of be aware of what we're thinking about and solutions that we need. And that you can be actively involved in it. And hopefully that is a seed for our idea and develop it further into flight hardware, but hopefully it will be a seed for you to feel accomplished. Even if you don't make it the top 5, you did make it through the cut, and it's very commendable. And I hope you're encouraged by it, and maybe you can apply for more challenges in the future.
Well put, Justine, and wise words for all competitors in this challenge. Thank you. Well, that's been a really excellent introduction to this. How about with no further ado, we move on to the next slide. We're going to go in order here from our first place team down to fourth place. But Jason, you want to take it away with your presentation?
Sure. Okay. So This is the intro page. It's kind of an overview of the static stages of the mechanism. So the title, there's an Easter egg at the end. I'll say what it is. I'm sure everyone will figure it out. So the title, Tossed in Space, Scissor Spring Shot, and Warning Will Jettison. So the name Scissor Spring Shot is derived from some of the components. So you can see there's a scissor jack as the most visible component. The red, long, skinny items in the middle diagram where it says powered up, those are springs. They're constant force springs, and I can do a demo of those at some point. And then shot is kind of alluding to a slingshot, the elastic style, not the David and Goliath leather and string style, but the kind where you usually use an inner tube or some sort of rubber. So slingshot. So, and then let me just talk about my motivations for how I was narrowing down and constraining the solution. So one thing I wanted is we had the 500 watt power limitation, and I didn't want that to limit the velocity. So that meant, well, I have to take that 500 watts and turn it into potential energy. So that was one of my solutions. I had to figure out how am I going to store that potential energy. Another one is I wanted to build it in the small scientific airlock. So if it would fit in the small scientific airlock, then it would fit in the big one. It could also be scaled up. And I wanted it to be easy to use with no tools required in order to install it or use it. So in order to maximize the velocity, there's two things you need to have for a given weight. You need to maximize the force, which comes back to our potential energy, and the distance over which that force is applied. So that's basically your runway. The longer your runway, the faster you can get your velocity. And in order to get that velocity, we have to come up with some sort of linear motion mechanism. And there are lots of choices there as well. So there's rack and pinion, there's a lead screw. Lead screws are pretty slow, but they're powerful. The rack and pinion, that's also kind of slow. Direct drive linear motors, induction motors, those would require a fast charge like a supercapacitor or a large bank of batteries. So I kind of shied away from that just because of the bulk. I also wanted it to be very compact and maximize space that we eject. And also there's ladder cascades, kind of like fire truck ladders or like home maintenance ladders where you pull on the rope and the pulley extends the other one. I've seen that used in robots before for things that need to reach, but that ended up being a little bulky. And you would have at a minimum 2 cables to pull up those different sides, possibly even 4, and keeping cables in sync would be kind of troublesome. You'd need some tensioners and possibly multiple motors. And I just felt it would get a little bit too complex. So ultimately I settled on the scissor jack and the constant force springs. So if we look at this picture, the idle stage, that's what stage this mechanism is in most of the time. If you're loading it, if you're stowing it, if you're mounting it, it's idle and nothing's under tension. There's no potential energy. It's not dangerous that it's going to like eject. So it's just idle. Powered up stage is when the scissor jacks have fully extended and they've stretched the constant force spring. So all the potential energy is there ready to go. And there is a mechanism, a rotary electronic latch holding the bottom of that pod, the orange pod. And when it lets go, that's the third state. It jettisons, the egress hatch automatically opens and the contents fly out with inertia. So those are your 3 states. And you can also see that 4 shades of blue, those 4 different slides, and that's to constrain the pod. So you don't rotate about the X, Y, or Z axis. It also prevents movement on the lateral X or Y axis. So the only way that pod can move is straight up and out. So it helps provide rigidity and control of that pod. So you've seen the pictures and it'll probably make a little more sense if we see it in action. So the next slide, we can play that. It'll repeat 3 times just so that your eye can look around at different events as this occurs. So you can see first it loads, then it lets go, and the pod shoots up and the doors automatically open. And the loading, when the scissor jacks are extending, that's actually sped up based on 500 watts and the amount of force that we're loading into those springs. It would take about 2 minutes and 20 seconds. But the ejection speed of that pod is actually real time. That's 12 meters per second. And that's assuming we used 24 springs. In this video, there's only 8, just to not clutter up the picture. But if you loaded that with 24 springs, it would go at 12 meters per second. 8 springs would be 7 meters per second. And so that also allows configurability. So depending on mission requirements, you might not want it to go 12 meters per second. You might not need that. Maybe 8 springs is fine, and the other ones can be backups or spares. Also, you don't have to extend fully. That was extended 1.21 meters. You could extend half of that, and it'll just slow it down a little bit. Or you could also drop that 500 watts to say 100 watts. And instead of taking 2 minutes, it'll take 10 minutes. So it all depends on the mission requirements. Maybe there's an experiment going on and you don't want to draw 500 watts. So it's very adaptable. So let's look at the next slide, and it'll just show some of the part names, the component names. We have 3 different slides of that. So yeah, so on the left here, we have the pod, the jettison pod. And I won't go over every single little part here. I'll just talk about some of the key parts. If you look at the bottom middle of the jettison pod, there's something called the spring and shock block. So that has a compact shock absorber on each corner. So when it goes to the top, it'll stop. It has a shock absorber just to slow it down a little bit. Most of your mass will be continuing on out into space. So it doesn't have to stop that whole weight, just the weight of the pod itself. And also that's where the springs attach. Another key part on the upper middle of that pod, you can see the egress hatch latch and the egress hatch latch pin. So those egress hatches are actually by default open. They have springs in the hinges. By default, they're always open. You would have to push and hold it down for it to stay closed. But the egress hatch latch and the pin, those push it closed, and we'll see on another video how that mechanism holds that closed. On the right is the motor mount. So you can see in red, we have a motor, we have a gearbox reduction, and that's so that you can use 500 watts or even less, and the gearbox is slowly loading that potential energy into the springs. The aqua in the very middle, that's the electronic rotary latch. That's what you would see if you're going into like an office and you wave your badge and it opens electronically. That's basically what that is. It lets go and swings out of the way. And then on the right, we have 3 knobs for mounting to the slide table. So we can go to the next slide. Okay, the bottom left, you can see just a piece of the reduction gearbox, and there's a gear coming out which attaches to the powertrain, and the powertrain is there to transfer power from the gearbox to the lead screw. And there are actually 4 lead screws that are around the perimeter of the pod, the bottom of the pod. And the reason there are 4 is they're all connected with miter gears. They all move in sync, so that way your scissor jacks all move together. You don't have to worry about sync issues. If they all are going up, they all go up at the same rate, they all go down at the same rate. On the right, we can see again the red springs, the constant force springs. The blue, shades of blue, that's a sliding track, just kind of like a drawer track. It just goes up to constrain that pod. And let's go to the next slide. Okay, so on the left, we have a close-up looking straight down. So you can see there's a stop. That's basically an aluminum and rubber stop so that those shock absorbers have something to hit when they arrive at the top. You can see again the constant force springs. And then on the right, this is underneath. We haven't seen underneath yet. This is the loading hatch. And you have 2 squeeze levers, kind of like you'd have for a glove box in a car. You squeeze that to open the hatch, load it, squeeze it, and put it back in. So we can go to the next page, which will be a video of how the egress hatch and those pins push the door closed. So you can see there's a lever mechanism, a 3-part lever. One part is sliding on the side of the pod. There's a linkage, and then there's another part attached to the hatch. So it just closes those lids. And this part of the video is just a small repeat of when it's coming back to dock, back into the idle stage. We can go to the next slide, which is an animation as to how you would actually load. So you can manually open that rotary latch with a little button. You swing open the motor mount with more squeeze latches, and you take off the loading hatch with the squeeze latches, and we're just throwing in an old lunar rover tire in there to eject. And you can see again those three knobs on the right. That's what you would use to mount to the slide table on the scientific airlock. And then the next and final page is another video. And this shows the jettison unit being attached to the slide table and the scientific airlock. So that green box is the scientific airlock. We swing open the inside door, attach the jettison unit to the slide table, and then it closes the door. They depressurize it and swing the door out, and it's out in space. And so those were all of the slides for this part of the presentation. Thank you.
Excellent. And these are some fascinating animations, Jason. Thank you. At the end, I will touch back on your experience of going through these, but for now, why don't we move on to our next competitor? And before you start, Craig, I'll mention that it looks like we've had some new people join the webinar. So in case you didn't hear before, please use that Q&A section at the bottom of your screen to put any questions in you'd like to ask towards the end. We prefer that to the chat so that I can actually see them to ask them. And yeah, with that, Craig, take it away.
Well, can you hear me?
Sure can.
Okay, good. My solution was conceived of more of a beginning to end concentration rather than all the fidgety parts. But I took a look at the HEL interlock and the solution was, obvious to me. It's just like a pipeline. You make it into, uses a pig to clean it out. So I started with the solution and I worked backwards to design how this would work and then went from there. And I did too also use the scissors approach. I didn't start there, but that's where I ended up. If I could go on to the next one. And the design principles is what guided me. I wanted to keep it just as simple as possible. And just like a pencil and a hammer and a wrench, they're simple. They do a specific job. And there's no ambiguity in design. And that's a principle to keep it in mind. And I get that from my aviation background. Use a minimum amount of complexity to accomplish the task, even though overall you might end up with something in a total very complex, but this is a small part. If you could go on. So basically, like I said, I went from the whole process from beginning to end. And with mine, I call it the pig, and it's collapsed and it sits in a storage shell right next to the hatch, and a crew member can turn a handle, pull it out and lock it in the airlock. And the airlock has been modified for some guide rails and stops so it doesn't keep going out into space. And the electrical connections are made. So there's not a lot of alteration at all on the airlock, and there's no slide table in there. So if you go to the next, please. And this basically is just a view of what it would work like. Of course, the waste bag is going to expand when you open the outer hatch as far as any residual air. And it's not a bad thing. It keeps it from floating away before it's kicked out. And the object, of course, is always to conserve as much air as possible. It's a resource that you just can't find up there. And I think this is pretty explanatory, but move on to the next one. Now there's some of the component parts. Basically, the front plate is static, and it has everything that's on it that controls it is on that front plate. And the pig is the only thing that actually moves along with the scissors in there. And you got return springs on the solenoid, and I haven't shown it, but you have some other return springs that mentioned in my text. And what that does is it does its job and it collapses. Now it is also selectable as to the force. That's why I'm using 4 different solenoids of different values actually. And I figured that 1 to 3 meters per second would be plenty. There's less the inertial force affecting the spacecraft, and my suggestion was to put it on the middle part where the airlock's at, near the center of the moments, so that you're not affecting the spacecraft. And move on to the next one. Now, these are the different features in there. And in other words, you select only what you need in an amount of force, and you have to make a judgment as to the mass. You can determine some of that in advance before they take off or make the flight. And but I also included a control panel, but when it's not being used, it doesn't draw any power at all. And everything in the control panel, which I show, is condition evident. In other words, like a cockpit of an airplane, you're looking to see at a single glance. You're looking at lights, but you're also looking at switch positions. And you just take a quick glance and you know what the story is. I do have a touch screen in there, but I put it in a just an ancillary fashion. In other words, a checklist to come up. So I'm thinking in terms of how the crew uses this. And I spent a lot of time working on that. If I could go to the next one, please. Now that's the camera view. You have a camera on the outside, which I'm pretty sure there's probably one on the hatch anyway in the spacecraft. To not do that would probably be a bit negligent, because you'd have to send somebody out to fix it in case it's stuck open, and you'd want to know that. And also a lipstick camera actually in through the part of the scientific airlock, so you can take a quick glance and make sure that the thing you've got what's in there and it's working. And the hatch over interlock on the left-hand side. Basically, there's an interlock to control the outer hatch to make sure you're not firing this thing with the outer hatch open. And if for some reason there's a jam or a sticks and you need to eject something and the interlock gets in the way, you got a simple little plug you put up there into the hatch interlock as an override. So your circuit is complete. And you select the force, you can select, it's pretty much explanatory. I tried to make it that way. So all in all, tried to keep it just as follow my guidelines, and I went back and I looked at the original problem many times, and I changed some solution sets, but I started with the vision of the solution and reverse engineered it, and that's how I got there.
Excellent stuff. Thank you, Craig. Love to see simplicity in these designs, so it's fun to see how you came to this solution. Before we move on to the third place team, I mentioned before that this is a bit of an open discussion amongst our winners. Did anyone have any thoughts on the first 2 submissions before we move on to the third one? And if not, no worries. We can also stew until the very end. So with that, I'll pass it over to you, Ross, and just ask that you let us know when to advance slides here and when you want us to start videos. Some of them are automatic, but you might have to do a little manual coaching. Thanks.
Okay, sure. Okay, so good afternoon, everyone. Once again, I'm Ross, and I am the designer and the inventor of the S1224. Next, please.
You go to the next slide there.
Yeah, yes. Right. Now, The challenge, as stated in the HeroX website, is to generate detailed mechanism designs for ejecting non-recyclable materials from a spacecraft during a crewed Mars mission. This statement, combined with the challenge criteria, has led us to a solution that caters all of the challenge requirements and even more. So after almost 2 months of learning how to use AutoCAD and Fusion 360, next slide, please. I have arrived to a breakthrough that is engineered to accommodate virtually all kinds of shapes given that the projectile fits in the entry of the launcher. The SBL-24 is designed in a way that values astronaut and spacecraft safety while also being capable of its designated job. It is efficient and versatile in the sense that it doesn't use any kind of consumables other than the electricity and elastic energy of the springs. It can be used in missions that require satellite deployment and launching experiments in space. It can also be used on the surface of Mars or any environment with or without gravity and with or without atmosphere. Now, I know it looks really complex and it has a lot of parts, but I couldn't just risk leaving out features that will help protect both the astronaut and the spacecraft from errors and failures. Next slide. Now, the SL24 has a lot of features, but I will only go over some of the most important ones. These are some of them. One is variable spring tension, collapsible frame, 4 independent launch systems, automated mechanical locking system, coaxial extension springs, and coaxial high power compression springs, 4 times linear actuators, 4 times fail-safe manual reloaders, removable trigger systems, replaceable springs, integrated lubrication ports, resettable guide sleds, extendable launcher arms, 8-corner silicone rubber padding, and more. Next slide. Now, in this section, I'll discuss about the reasoning behind the design decisions that were made in the project. These are questions that start with why, and they help in shaping the way the end product and its features came out in the end in order to properly accommodate the challenges, criteria, and requirements. This is the reasoning in design. First one is, next slide. Yeah. Okay, first one is why variable energy. Now, this decision was influenced by the fact that we are uncertain of things and we don't have a final plan and design yet. And considering the nature of space missions, we are also uncertain of the events that may unfold during its duration. I'm sorry. So having the ability to change the energy and exit velocity of the projectiles will be a great advantage to the astronauts. And that will be operating the mechanisms in the future. We also wouldn't want to damage the launcher and the airlock by needlessly setting the spring tension too high because this launcher uses a lot of powerful springs. Second one is why collapsible frame. This decision was influenced by the need to create compact and versatile solutions. It's like the saying, getting 2 birds with 1 stone. By collapsing the frame, you will be able to save space when the launcher is not in use, and you'll also be able to fit it into smaller airlocks. And yes, the launcher is designed to work, even if it's fully extended, fully compressed, or somewhere in between. The only thing that changes is its internal volume capacity it can effectively launch. When fitted to the HAL scientific airlock, the SBL-24 can accommodate a 9.4 by 9.4 by 15.5 inches of volume. Next one is why make independent launch systems? One word, redundancy. Just like what I mentioned the first reason, we are uncertain of how the mission is going to unfold. By having multiple independent systems, the astronaut will be able to jettison trash and offload mass even if one or more of the launch systems fail. Also, by having separate launchers, differential thrust and a wider range of exit velocities can be achieved simply by disengaging launchers. Next, please. Now, another one is why make automated locking systems? To prevent human errors and accidents. The locking system also protects both the astronauts and the spacecraft from catastrophic failures in case such as a launch system fails or a trigger system fails. Next is why include fail-safe manual reloaders? Just like why make independent launch systems, this is to ensure that the astronauts will be able to use the launcher even after linear actuators and even electronics fail. This launcher will be able to operate even if the spacecraft loses power, as long as you can open the external hatch. It doesn't need electricity, it's entirely mechanical. Now, next one. Why coaxial springs? Springs are like mechanical batteries, and with batteries, you'd want a high capacity high energy density as much as possible in order to save space while also having a lot of capacity. By utilizing coaxial springs, we were able to get up to a theoretical amount of 77,000 newtons of force, making the launcher capable of launching 500 grams or load to 100 meters per second or 360 kilometers per hour, using only kinetic energy and elastic potential energy equations. And just to clarify, the SVL-24 can launch a 50 kilogram load over 10 meters per second. Also, it is important to take note that the models and the plans you see here in the presentation and the submission aren't final yet, but they are already a working proof of concept. Next is why make removable trigger systems? Now, this question lies in the realm of maintenance and repair, and by having removable trigger systems, the astronaut will be able to easily maintain and repair these complicated systems. In fact, the entire launcher assembly can be disassembled for easier maintenance and repair. Next. Now, why include lubrication ports? Those lubrication ports found in the base frame of the launcher are meant for the pull to disengage lock and the tension resetting system for the extension springs. Those parts of the launcher are going to be difficult to access, thus having ports like those for maintenance and lubricant top-up are important. And then, why resettable guide sleds and extendable launcher arms? Next. These features go with the collapsibility of the frame and is meant for the versatility and wider range of options in terms of projectile shape and volume. The guide sleds are meant to hold the projectile in place, and the launcher arms are meant to propel the projectile forward. They are meant to ensure that the projectile is properly held in place so as to avoid jams and entanglement. And finally, why only design 5 inches of travel for the launcher arms? Now, this is to protect the spacecraft when all safety systems fail. One of the biggest risks in this kind of launcher is the launcher arms and the guide sled striking the outer hatch. And that might cause damage, a fatal damage to the spacecraft, and we would want to avoid that. By limiting the travel to 5 inches, this kind of scenario is made absolutely impossible. This is because the solid height of the extension springs will simply not allow the arms to move forward, let alone the guide sleds touch the hatch. And now, next slide, please. And now we go on to a quick demonstration of the firing procedure. First, in order to load the projectile, you push and turn the launcher arms. Next, you put in the projectile. Next is you reset the guide sleds and extend the launcher arms if needed. Next is to close the internal hatch. By closing this hatch, you disengage the automated locking system and the linear rails are ready to fire. Next is to remotely open the external hatch that will pull on the synchronizing bar, which in turn sets free the secondary trigger. And when that's done and the primary trigger is free to rotate, the launcher fires. After firing, you remotely close the external hatch. And once closed, the linear actuators will automatically reload the launchers if auto reload is turned on. And now, if the internal hatch is open, the automated locking system will once again engage. And lastly, we go on to the materials. Next page. All in all, there are 6 kinds of materials used in this launcher, some of which may change in future improvements of the design. For example, weight improvements. First one is titanium grade 5, which is used for most of the load-bearing parts. Next is aluminum 6061 for the base frame and other non-load-bearing parts. Carbon steel for most of the important parts in the trigger system. Alloy and chrome silicon for the springs. Stainless steel for over-the-counter parts. And finally, silicone rubber for the 8 corners of the launcher. Next slide. For a recap, the SWL-24 is a launcher capable of ejecting a variety of volume, mass, and shapes. It is safe for both the astronauts and the spacecraft, offering full control of every process in its operation. I appreciate you taking the time to listen to this presentation, and that's it for my turn. Thank you.
Excellent. Thank you, Ross. Appreciate it. We've seen some really talented entries, and hopefully y'all are seeing that they've all approached it from very differing perspectives. We'll see in these last 2 some additional attempts at addressing this problem, and they've used their own unique approaches while having some themes in common as well. So with that said, let's move on to our 4th place team. And 4th place might sound like it's further down, but the truth is that this challenge actually had only 3 prizes originally. And these final 2 teams were of such high quality that the challenge judges wanted to award them as well, give them recognition, and also let them know that there was incredible value in their submissions. So with that, let me pass it off to Team Aggie Arrows. Take it away.
Yep. So first, I'd like to thank everyone for being here and taking time out of the day to listen to our presentation. And so we are the Aggie Arrows from Texas A&M, and we will be presenting the SLEM, or the spring-loaded ejection mechanism. Next slide, please. Okay, so I know there's a lot of commonalities between the submissions so far, and most of them had springs, and we are no different, but we spent approximately 2 weeks of the competition making sure that we have an idea that is the most optimal as well as the most energy efficient. And so to do this, we started with a decision matrix. And the first 2 ideas to be eliminated were the explosives and the flywheel due to their high risk towards the crew and the spacecraft. An air release system or air cannon seemed to be the simplest solution. However, it was eliminated due to safety concerns. As the air release system launches trash multiple times during the mission, air is being slowly released into space, thus it's basically a non-renewable mechanism. The remaining 4 were discussed in greater detail as we weighed out the pros and cons of each system. The induction coil was eliminated for 2 main reasons. The first is that the estimated power draw would be well over the allotted 500 watts. And the second concern we had was that the mechanism must be electromagnetically shielded, as the magnetic field may interfere with onboard equipment. The electromagnetic system was also eliminated since its function is similar to the springs, but it still required the aforementioned electromagnetic shielding. Ultimately, the springs were chosen for its simplicity, cost, safety, and high TRL. Next slide, please.
To operate the mechanism, first, an astronaut will place the waste against the launch plate. When the payload is in position, the astronaut will stretch the 3 polymer retention bands that are originally attached to one standoff around the other standoff and attach the loop in the band to the release hook to keep the payload flush with the launch plate. After the waste container is properly secured, the system will be primed by pressing a green button on the back of the base plate. Using either a timer, onboard sensor, or a different signal received from the HAL airlock, the SEM will determine whether or not the airlock door is open. When the system detects that the outer door is open, a signal is sent to the motor to begin compressing the springs. An encoder on the motor will ensure that the springs have been compressed to 1 inch. And when it has reached that 1 inch compression, it will then release the springs and the waste will then be pushed out. Additionally, when the motor is wound, a signal is sent to simultaneously release the retainer bands and disengage the gearbox clutch. Disengaging the gearbox will allow the springs to unwind rapidly as the springs decompress, launching the payload. This separation from the motor also avoids excessive torque on the motor from the high loads caused by the springs. After launching the payload, the gearbox will re-engage, allowing the motor to re-spool the strings to its original position and prepare for the next launch. Next slide, please.
All right, so we also had the astronauts in mind when designing our mechanism. And so we designed our mechanism to be disassembled easily for repairability. The rails for the mechanism shown here can be released allowing easy access and separation of the mechanism components. Another thing we also considered was that the mechanism might slowly leak off temperature into space as heat through radiation, and this might affect our spring constants, as well as affect the material properties of our mechanism. But then with some quick calculations, realized that the temperature change was irrelevant, as the mechanism will only be exposed to space for around 2 to 3 minutes. And in that time, it would not, the temperature would not drop significantly enough to make a difference. Next slide, please.
Lastly, dangers posed to the crew are very minimal due to the nature of our design. Only hazards with mishandling of elastic retention bands, which the crew will be taught to handle properly and warned about. As the launching of waste is automated, astronauts will face no exposure to the compressed spring or motors during operation. Astronauts will only need to interact with the electronics by pressing one of 2 buttons in the base plate to prime the mechanism for launch or for unpriming. Because of the low force at which the trash is launched from the mechanism, the spacecraft will not be at high risk when the mechanism is operating. A significant recoil from the waste is unlikely. And that's everything I have. Thank you.
Excellent, thank you guys. And lastly, Jeff Morris, who could not join us, was our other 4th place tie. We only have this slide from him, but his concept actually did use a slightly different method by having compressed gases of different kinds being used in a piston. So his is called the CO2 trash launcher, or COTL for short. And the CO2 was envisioned to be something that was taken from the cruise ship if there was any unused CO2, and it would be used for priming the piston with condensed air, using it to expand out and push that sort of orange polygonal ball out. That red retention band would break away in some ways, but remain attached to the launcher. And then the ball would move outwards, the ball of trash. The compressed air would also be used to pull the piston back into its original position. And so in some ways it operates similarly to the ones we've seen. It just happens to use compressed air as its mechanism, or sorry, compressed gases as its mechanism. And we found that to be worthwhile, another 4th place win. So congrats to Jeff too. With that, if you want to go to the final slide here, I just want to thank you all for joining us and presenting to the public. Like I said, we wanted to give you all a lot of kudos and recognition at this point. You've all worked so hard on this. We've heard varying challenges of people having technical issues, to having to organize teams across the globe, to having to organize teams of over 10 people. And with that, I have one question I want to throw to the group if you guys don't have any immediate thoughts for each other. And it's, what advice or what lessons learned do you have for the public that's watching? You each had such different experiences, whether it was managing a large team or actually dealing with not being on a team and everything resting on your shoulders. So any advice or insights from any of the competitors?
Make it fun.
Well put, Craig.
Yeah, make it fun. Really. Nothing ventured, nothing gained.
I like that very much. Thank you, Craig. Anyone else?
I think that's a pretty good point. For us, since we have such a large number of people on our team and we're spreading it across mostly freshmen in college, it was difficult at first to maintain engagement with everyone. But once we started getting into it and people got more interested and realized how fun it was a lot easier to maintain the group as a whole and ensure that work was being done at all times. And even after a 2-week period of looking at the various potential ideas, we still kept coming up with more because people were thinking in their own time and not necessarily just when we were working together as a team. And so I believe that having fun on this project helped facilitate everyone thinking to do it in their own time, not necessarily just thinking of it as like another thing to do for a resume, and actually something they want to do personally and not just for benefit externally.
Yeah, I would add that the more competitions you can do, the better you'll get. Each submission will improve on the next, and every iteration you're going to learn more techniques. So like this competition, I improved my animation skills a lot. The previous one, I used a tool called Tinkercad, which does not animate, but I animated it by taking a picture, moving it, taking a picture, moving it 300 times per second to get a minute of video. So that was very time consuming, but every time you do one of these, you're going to learn a new tool or new techniques. And I think it's important to just do a lot if you can.
Oh, okay. All I just want to say is that teamwork is important, and maybe if I didn't solo it, maybe I could have gone for a better design. So yeah, teamwork is really important, and collaboration with your teammates is the most important thing in this kind of competition. So that's it.
Great stuff. Thank you all. And maybe Jason and Miko can connect afterwards to talk a little bit about their 3D animation experience, trade some tips here and there. Any thoughts, Miko?
Well, this was pretty special for me because I have never done something like this before. So it was very interesting learning experience from how this kind of animation works and how all these things work. And Ross really had to help me with a lot of that. But yeah, it was really fun. Yeah, I learned a lot.
That's great to hear. Thanks, Miko. We've got just a few more minutes here. And again, a reminder to the audience, if you have any final questions, put them in the Q&A section. I did ask the main one I was sharing, which is just thoughts on how to do better. But then otherwise, I might also loop in the NASA team back here at the end and say, is there any question anyone has for the NASA folks that are on this call? You got to meet them during the pitch sessions, but this is one final chance for us all to say congratulations to you and to just can come together. So any questions for the NASA team or vice versa?
I'll jump in real quick. Just to add, I get to see a lot of winners webinars, different challenges, different platforms. One thing that stuck with my team is for a different platform, someone that's won so much, it's become their full-time job. Like they just participate in challenges and actually have got hired by that platform since. I don't remember the exact percentage. I think it was 70%. He spends 70% of his time, it was definitely more than half, learning, and only something like 20, 30, 40% of his time actually executing. Because in order to stay fresh with the constantly changing technology, he has to keep staying on top of his game. And so it's funny, we, especially in America, think like, I'm really only working if I'm executing, if I'm doing something. But he's actually making significantly more money than anyone else, like than the average in his country, by spending most of his time learning and only a little bit of his time executing, because he's so much on top of his game that he's able to win the few times he's doing it. So my recommendation based on his experience is, if you want to keep competing, is keep learning, keep doing new things, spend a lot of time learning, keeping up with technology, because that's what sets you apart.
Great advice, Ryan. Thank you. What I'm taking away from this is learn and have fun. So if that's what I take away, I'm okay with that. Hey, Steve.
Hey, well, yeah, thanks again for such great submissions and great ideas. We're going to try and move the ball forward. So does anybody mind if we move the ball forward, start trying to make prototypes, if we get your contact information as we go forward for questions and answers, if we want to try and make some prototypes or move it into something that's, from concept to development. So I guess the question I'm asking is, you guys don't mind if we move forward, and if we have questions, we can contact you later. Is that okay?
I'm all for it. I'm only 2 hours away from Kennedy, so if you have any resources there, that'd be really convenient.
Hey, I'm in Florida too.
Cool.
Great. Everybody else okay? Okay.
Great stuff, Steve. We love to see it. Well, we've got one final minute here. I think I would just say thank you all again for joining today's call. And if you have any further questions, you're welcome to keep in touch with me. That's about all. I think just have a heads up for any final communications about the challenge, but let's just say one last time, congrats to all of you guys. And if you want to give each other a little air applause for each other's efforts, you've all done a really amazing job, and this has been a fun challenge to see. So thank you for your time.